All right, good morning, everybody. So I want to talk about generic queues using linked nodes today, but before I do that, I'd like to go back and review the stack implementation with nodes. So I'm just going to quickly go through lecture 22, and I'm just going to skim over it just to remind you how these work. All right, so I want to make a node using a bunch of linked nodes instead of using an array to store the elements. Okay. So remember, in a node-based structure, you've got this type called a node. The node stores a reference to an element, right? And it stores a reference to the next node that's deeper in the stack, in the case of a stack. Right, so if you were to draw a picture of a stack with one element on it, and you're implementing the stack using nodes, then what you end up with is a stack with one node. Right? So that whole thing there is a node, right? So the block plus its arrow is a node. Right? Inside the node is the element, and the arrow is the reference to the next node in the stack. Right? Now there's only one node in this stack, so that reference is null. But so there's your element, there's your link. Right? So remember that reference, we often call that a link. Now if I'm going to push an element onto the stack, right, what I want to do is I want to make a new node and I want to stick it up here. Right? And then I want to make it point to the original, the previous old element on the previous old top element. Right? So we make a new node. Right? You set the link of the new node to point to the current top node, right? So that arrow appears, right? And you say that the next node to B is the A, right? Then you move top so that it refers to B. Right? And then you add one to the size of the stack. Right? So when you're using these linked structures, the trick to using these is to remember that you have to set that link to point to the right node. Right? And a lot of the algorithms that work on these linked structures work by either following links to nodes or by manipulating the links so that you can point them to other nodes. So for example, you can, let me put one more. I can take this stack and I can reverse this stack. Right? So the way you reverse the stack is you just reverse all of these next links. Right? So I make, starting with the C, because it's at the top, right? I'm going to make the C, its next link, point to nowhere, to null. Right? And then I'm going to go to the next node, and I'll make the B's next link point to the C, and then I'll go to the A and make its next link point to the B. Right? And that effectively reverses the elements in the stack. Right? So all these algorithms that work on node-based structures are traversing from node to node, or manipulating the links between nodes. Is that all? I just want to quickly, let's just jump. We don't need that. I just want to quickly jump to the implementation. Where is it? OK, so here's push. Right, so when I push an element onto the stack, I make a node. Right? I set its next link to point to the current top of the node. Right? And then I just set the top. I set the top of the stack to refer to n, right? Because that's the element. That's the node holding the element that we just pushed onto the stack. Right? And then you increase the size of the stack by 1. Right? So the implementation is really straightforward. If you look at the code that's here, you can. There's a constant number of operations needed. Right? So nothing here depends on the size of the stack. Right? So that operation happens with complexity big O1. Right? If you pop, so to pop the stack, right? You remember what the top element is, right? Because I'm going to remove that node, so I need to get the element out of the node so I can return it back to the caller. Right? You then take the top and you move it down to the next one, right? So you just follow the link. Right? So top.next, that's a reference to the second element in the stack. Right? So the first element is now equal to the second element, right? Or the top of the stack now points to the second element in the stack. Right? And then you decrease the size of the stack by 1. Right? The important line here is that one right there. Right? So you have to get used to following these links from node to node, right? And manipulating the links. Now again, if you look at this code, right, there's only a constant number of operations here. Right? If statement here, assignment, arithmetic, and a return statement. Right? So the complexity of that is also in big O of 1. right? Now remember, in a stack, so for push, if you had an array-based stack, right, every once in a while you have to resize the size of the array, right? So the worst case complexity for push on an array-based stack is big O of n, right? I have to make a bigger array, then I have to copy the n elements currently in the array into the new array, right? Here it's always big O1, right? All right, so now that we've got a quick refresher of the using nodes in a stack, we can see how to implement a node-based queue. Right. Now there's only one small difference between a linked node-based stack and a linked node-based queue. Right. So in a stack, the nodes are added at the front of the chain of nodes. Is that right? Yeah, in a stack, so our node-based implementation, we add to the front. Right? In a queue, we add nodes to the end. Right? So that's what a stack, if you draw a picture of what you're doing in a stack, right? So there's a stack of size 1. Right? When I push an element onto this stack, right, then you can think of that as adding a node to the front of this chain of nodes. Right? You push another element, the C, right? I'm adding to the front of this sequence or chain of nodes. Right? Now with a queue, remember, people get in at the back of the queue. So in a queue, right, you add the element at the back of the queue. Right? So when I start with an empty queue, you have one element in it, right, or one node. When I add, or when I enqueue another element, right, it shows up at the back of the queue. And when you enqueue the third element, again, it shows up at the back of the queue. Right? So notice that when you enqueue, you're manipulating, you have to do a few things. Well, you have to do a few things. One of the things you have to do is you have to always update what element is at the back of the queue. Right? So you have to update this field back so that you can remember where is the back element of the queue. Right? OK, so let's look at the implementation now. So remember, the implementation is almost exactly the same as a stack. Right? So we have a linked queue of some generic element type. Right? It's going to implement our queue interface. Right? We're going to store the number of elements in the queue. Right? We have front and back. Right? So front is analogous to top in the stack. Right? Back, and now we have to remember where the back element is as well. Right? Because in a queue, we're doing things at both ends of the queue. Right? Things come out at the front, and things come in at the back. Right? So I need both of these references. Here's our node class. That should be static, sorry. I guess I have to fix the notes too, because that's where this came from. So that's a static class, static inner class. So what does our constructor do? Well, our constructor for an empty queue sets the size to 0. Right? We're going to set front and back to null to indicate that there is no front element and no back element. Right? How do you get the front element of a queue? Well, you just return the element that's sitting in the front node. Right? And to get the back element, you just return the element that's sitting in the back node. Right? So that's nice and easy. Enqueue. Let me go to dequeue. No, I guess we have to do enqueue. All right. So for enqueue, it's a little bit more complicated than pushing an element onto a stack. The reason it's more complicated is because there's a couple of special cases that you have to take care of. All right, so to enqueue an element, I'm going to make a node, right, to store the element that we're going to add to the queue. Right? Now, ignore the first two for now. Okay? So let's just look at the last statement in the else part of the if statement. Right? I'm going to make an element, right? And then I'm going to add it to the back of the queue. Right? So the way you do that is you say this dot back dot next is just equal to n. Right? So the next link for the current back of the queue, right, that now points to the new node that you just added. Right? Now, after you do that, what do you have to do? Well, I just added a node, so I have to update this dot back. Right? And then I have to increase the size of the queue by 1. Right? So that's what you do most of the time. Right? Most of the time, you only update this dot back dot next. Right? And then this dot back. right? So add something to the end, and then update what the end of the queue is, right? So most of the time, that's what you do. Now, the problem is we're keeping track of a second piece of information, right? We've got the front of the queue as well that I need to keep track of, right? And that's why you have these two special cases, okay? So if the queue is empty, right? Remember, the front and the back of the queue, the front and back fields, they're both null in an empty queue, right? As soon as you add something, right, you have to update the front field now, right? Because now the front of the node, the front of the queue now points to that one element you just added, right? The back of the queue also points to that one element you just added, right? So you need that special case there in order to update this dot front, right? Which you normally don't have to do when you push something, when you enqueue something into a queue, right? Normally you only update the back of the queue, right? Well, there's one more special case, right? Because it turns out we're actually storing two extra pieces of information, right? We're not only storing where the front of the queue is, right? We're storing what the front of the queue's next element is. And we store that in this dot front dot next, right? So if the queue has one element in it, right, then I need to say that the front element now, its next link now points to the new queue, the new node, right? So now I'm updating this dot front dot next as well, right? Which you normally don't have to do, right? Normally you're only updating this dot back dot next and this dot back, right? But these two special cases are very easy to miss when you go to implement the enqueue operation, right? If you write some unit tests, though, right? So you write a unit test where you add something to an empty queue, you will catch that case, right? And if you write a unit test where you add something to a queue of size 1, you'll catch that case. And then if you write a unit test for where you add something to a queue of any other size, you'll catch that case. Right? When you're implementing these data structure methods, right, the unit tests end up helping you a lot. Right? So having pre-written unit tests really saves you a lot of time when you go to do your work. Right? Okay, so how about dequeue? So dequeue is similar to pop on a stack, except you're removing. No, it's similar to pop, right? Similar to pop, but again, because we're keeping track of two things in the queue, there's going to be a special case. Right? So dequeue happens at the front of the queue. Right? So most of the time, right, you get the element that's sitting at the front of the queue. Right? You move the front of the queue. Right? So you move it. You move that reference so that it points to the second node, right, in the queue. Right? So in other words, front dot next, I just follow the next point, the next field to go to the next node, and then you decrease the size of the queue, right? But you have to remember there's a special case kicking around. Because I'm keeping track of the back of the queue, right, there is one instance when I have to update the back of the queue, right? So if I remove all of the elements from the queue, right? So this is the case, so if there's one element in the queue, right, and I do this, right, there's now no elements in the queue. Right? So the queue is now empty. But that means you have to update this dot back. Right? You have to update this dot back now to make sure that this dot back now refers to no node. Right? So there's no more elements in the queue. Right? So again, if you're trying to implement this, then having unit tests around is very useful. Right? Try to dequeue an empty queue. Make sure you get an exception. Try to dequeue a queue of size 1, make sure that you end up doing that, right? And then dequeue a queue of any other size, and they'll catch the rest of it. It'll determine whether or not the rest of this is working properly. Right? So it's basically the same as a stack. It's just you have to now watch out for these special cases. All right. So I guess probably Friday, we're going to start talking about a linked list. And in a linked list, you're going to run into the same situation. Right? So in a linked list, you're also keeping track of the front and the back of the linked list. So when you're adding or removing stuff from a linked list, you're going to have to take care of these special cases. All right, so keep that in mind for probably Friday or Monday. OK, so let's look at enqueue. Right? So if you scan through this code, right, you'll realize that nothing here depends on n, right, the number of elements in the queue, well, except for the empty in the size 1 case. Right? But the general case does not depend on the number of elements in the queue. Right? So the worst case complexity of this method is big O1. Right? DQ is similar. Right? Nothing here really depends on the size of the queue, right? For a large queue, right? It's you just you do this line, and this line, and then the last line, right? So constant number of operations. So this is also big O1, right? So the complexity of NQ is in big O1. Now its worst case is much better than an array-based queue, right? Remember, in an array-based queue, every once in a while it's big O(n). Most of the time, it's big O1. Right? Now, the problem with implementing a node-based queue is that on average, right? So the average case complexity is the same as for an array-based queue, right? They're both O1. But if you count the number of operations that you have to do in a node-based queue, it's actually worse than for an array-based queue. Right? So when you go back and count what you have to do in NQ, right, you've got 2 if statements that you need to check, right? And then normally you're doing all of this as well, right? And you're also making a new object every time, right, which takes some time, right? So the average case performance of this is actually worse than the average case performance of NQ for an array-based queue, right? Because in an array-based queue, you're just updating a few, you're just setting an array element and changing the back field and the size, right? So average case runtime is actually worse. Runtime, that's not complexity, right? So that's runtime. Complexity is still the same, right? But if you actually time this thing with a stopwatch, right, your node-based queue is slightly slower. And the same is, so for DQ, right, we don't benefit or pay a penalty at all for a node-based queue, right? Worst case complexity is the same as for an array-based queue. Average case complexity and runtime is similar to an array-based queue. Right? So by going to a node-based implementation, we get this, we gain that part right there, right? So our complexity becomes big O1, right? Whereas in an array-based queue, the worst case complexity is big O(n). All right. So that wraps up stacks and queues. Well, that wraps up the implementation of stacks and queues. Any questions about queues at this point in time? All right. The next part here is generic methods. So we've implemented some generic interfaces, right? So that's an interface where you can, where the user is able to specify the type or a type or multiple types. Right? We've implemented generic classes. Right? So again, that's a class where the user is able to specify a type or types. There's also generic methods in Java. So a generic method is a method that has its own type variables. Right? So a generic interface has its own type variables. A generic class has its own type variables. You can actually go all the way down to the method level. Right? And so you can create a method that has its own type variables as well. Right? Now, you can put these things inside of a generic class. Right? Now remember, the class has its own generic type variables. The method will now have its own type variables. Right? For simplicity, I'm not going to do that. So I'm going to place our generic methods inside of a non-generic class. Right? OK, now you've got type variables on your methods now. Right? But every method is independent of every other method. Okay? So the type variables for one method are not the same thing as the type variables for another method. Right? Each method gets its own type variables, even if you give it the same name. Right? So it's like having a method, 2 methods having parameters with the same name. Right? The parameters for the 2 methods are independent. The type variables for 2 generic methods are also independent. Okay? So in other words, the scope of the type variable is confined to that method that you've placed them on. Generic methods show up. They often appear in utility classes that operate on generic types. Right? So arrays is the utility class containing a bunch of generic methods that operate on arrays. collections is the utility class that has a bunch of methods that operate on generic collections. And objects has some methods that operate on objects. Right? So there's a generic method looks exactly like a regular method with one exception. Right? When the type variables for your generic method, they appear inside of this less than and greater than bracket. Right? And they show up immediately before the return type of the method. Right? So in a generic method, you've got the type variables sitting in front of the return type. Right? Now, I want to make a utility class that operates on stacks. Right? So I'm just going to make a bunch of methods that do things to stacks. Right? Because our stack classes are pretty minimal. Right? They basically stack can only push and pop. You might want to do other things to a stack. I'm going to put those methods that do other things to stacks inside of a class, inside of a utility class. Right? So for example, I want a method that clears a stack, right? Removes all of the elements. Because our stack class and interface does not have that method. Right? All right, so how do you clear a stack? Well, you just pop everything off the stack. Right? Do you care what the element type is when you do this? No, you don't care what the element type is when you do this. Right? Okay, so here's my class, right? So public class stacks. Right? Notice that this is a common occurrence in the Java language, right? If you have some class like stack, right, and you decide that you want a utility class that provides extra methods for your stack class, then it's common to add a plural. It's common to pluralize the class name, right? That's why there's a collections with an S. It operates on collection classes, right? There's an arrays with an S. It operates on arrays, and so on and so forth. OK, so what does this look like? Well, I want to be able to clear any stack, right? So a stack of any type T, right? Any element type T. Right? Now, so that's a generic method. The class isn't generic, right? So there's no generic type after the stacks. Right? So this is taking in a generic stack. So I can place the generic type in front of the return type. Right? And this indicates this is a generic method. Right? So that's the only difference. Right? The generic type sits in front. Right? How do you implement clear? Well, you just pop everything off the stack. Right? So you could use a while loop. Right? So while the size is greater than 0, pop the stack. Right? The elements disappear because we're not keeping them at all. Right? We're not storing them anywhere. So the elements disappear, and then when the method is done, the stack is empty. Right? So nice and simple. All right. So let's try another simple method. Right? So I want a method called pushAll. Right? So it takes the elements from a collection. We could add another one that works on an array, but I only have one for a collection here. So it takes all the elements in a collection and pushes them onto the stack. Right? The methods do not remove the elements from the collection or array. Right? So all I'm going to do is I'm going to iterate over the collection, take each element, push it onto a stack. Right? Now in this case, the type of the collection, the element type of the collection and the element type of the stack matter. Right? So the element type of the collection has to match, question mark, the element type of the stack, right? So in other words, if I have a collection of string, I can't push that onto a stack of integer, right? The element types need to match, question mark, right, for the collection and the stack. Right? So here's my generic method, right? So I have a collection, right, of some type T, right? That's where I'm going to get the elements from, so it's called source. Right? I'm going to push them onto a stack, right? So that's where they're going, so that's called the destination. Right? I can only push elements of type T onto a stack of type T. Right? So it makes sense that these two types here match. Right? So that's T and that's T. Right? You don't want T and then U here, for example, right? Because that's probably not going to work. Right? If you have a T and a U, you're going to say I can take in a collection of some type like string, and then you're going to try to push them onto another stack whose element type is something else, right? Say integer. Right? That's obviously not going to work. Right? Now this is a generic method, so generic type shows up, and the generic type variable appears in the front. Right? Again, this is easy to implement. You just iterate over the source collection. right? So for each element in the source, push it onto the destination stack, right? So that loop does not remove the elements from source, right? It just iterates over the elements. Each element ends up being pushed onto the stack. Right? So nice and easy. Any questions so far? All right. What about popall? So popall is the reverse of pushall. Right? I've got a stack with some elements in it. I want to pop all the elements off and put them into a collection somewhere. Right? The methods. Why is that there? The methods do not remove the. I don't know why that's. I think that's a copy and paste error. Okay, so popall takes all the elements off the stack. So the stack will be empty after this method finishes running. Right? Again, like the previous example, right, the element types of the stack and the element type of the collection matter. Right? Whatever type you're popping off the stack, right, you have to be able to add that to the collection. Right? So for the time being, right, the element types must match. Right? Notice there's a question mark here, so I'm not quite telling you the whole story here. Right? So here's popall. Right? The source of the elements is the stack. Right? The destination, right, where the elements are going, is the collection. Right? Again, if I have strings in the stack, I can add those to a collection of string, right? But I can't add that to a collection of something else. Right? So that's a generic method. So generic type, the generic variable appears in the front. Right? And again, this one's easy to implement. Right? You're just going to pop the stack until it's empty. Right? So that's the same loop that's in clear. Right? While the stack size is greater than 0, pop the stack, right, and add it to the destination collection. Right? It's nice and simple. All right. Fourth method. So now I want contains. So contains is going to test if a stack contains a specified element. Right? So it's similar to contains for a list. Right? You're going to iterate over the elements of the stack. Right? If you find one that's equal to the searched for element, you're going to return true. If you don't find one that's equal, you're going to return false. Now, we're outside of any of our stack implementations. Right? So we're not inside the array-based stack implementation. We're not inside the node-based stack implementation. Right? So what does that mean? It means I don't have access to the array holding the elements in an array-based stack. And I don't have access to the nodes holding the elements in a node-based stack. Right? So now I have to use only the stack interface. Right? And what does the stack interface have? Well, I can get the size of the stack, I can get the top element of the stack, and I can push an element onto the stack. And that's all that I can do. Right? So I now have to search a stack given only size, push, and pop. Right? So that looks like it's going to be tricky to do. Right? So notice that it's inconvenient to implement because I don't have access to the private fields of any particular stack. Right? And I need to iterate. Right? I need to iterate. OK, so how am I going to do this? I can pop an element off the stack. Right? But if I pop something off the stack, I have to remember to put it back in later on. Right? Because I don't want to. Contains should not destroy the user's stack. Right? If you can imagine if you were calling a contains method and it blew up your collection, you'd be pretty unhappy. Right? So contains should not appear to change the state of the stack. Right? All the elements that were in the stack before you called the method should still be there, and they should be in the same order. Right? So I can pop an element off the stack, but I have to remember to put it back in later on. Right? Furthermore, the first element I pop off is going to be the last element I push back in. Right? So I'm going to pop the elements of the input stack onto a temporary stack, right, until the input stack is empty, right, or we find the element that I'm looking for. Right? When the stack is empty or you find the element that you're looking for, you then reverse the process. You pop every element from the temporary stack and push it back onto the original input stack. Right? And I claim that that will restore the original stack will restore the stack to its original state. Right? In other words, it'll leave the stack apparently unchanged. Right? So here's a picture of what's going on. So S, that's my input stack. Right? I'm looking for the Z in this stack. Right? I have to iterate over these elements, but I can't, right? Because I don't have an iterator in the stack class or in the stack interface. Right? And I've got, I don't have access to how these elements are stored. OK, so what do? So I make an empty temporary stack. Right? So I make an empty temp. Right? So I'm looking for the Z. So I'm going to pop the D, right? The top element, and I'm going to check, is that equal to Z? Right? So the answer is no, so it goes into the temporary stack. Right? S still has some elements in it, so I'm going to pop that stack. Right? So is the C equal to Z? The answer is no, so I'm going to push it onto temp. Right? S still has some elements in it, so I'm going to pop that stack. Right? Is the B equal to Z? The answer is no, so it goes into temp. Right? Still have an element, so I'm going to pop S. Right? Is A equal to Z? The answer is no. I'm going to push it onto temp. Right? And now S is empty. Right? So I know that does S contains Z is false. Right? Now, I have to restore S. So I need to reverse the process. Right? So here we go. Right? So starting with the temporary stack, right? There's stuff in the temporary stack, so I'm going to pop it and push it into S. Right? Still stuff in temp, so I'm going to pop it and push it into S. Still stuff in temp, right? I'm going to pop and push into S. Still stuff in temp, so I'm going to pop and push into S. Right? Now temp is empty, and S is in the same state as what it started in. Right? So you've got a method here that actually does change the state of the input stack, right, while it's working, but it restores it to the original state when it's done. Right? So it appears that it leaves the stack unchanged. OK, now if you do find the element along the way, so back here, right? So suppose you were searching for the C, right? So when you pop that element, right, you compare it to the input, you compare it to the element that you're searching for. Right? So if you're searching for the C, you'll do C equals C when you pop it out. Right? And that'll be true. Right? So as soon as you find out, so as soon as you find the search for element, you can stop this process, right, and then go to this process. So then unwind the process. Right? So it ends up looking like this. Right? So I have the result. Right? I'm going to start it with being false. So the element, so obj is not in the stack S. Right? I'm going to make my temporary stack here. Right? Notice that it's a stack of element type T, which matches the input stack. Right? And now I'm just going to pop everything off of S until I find the thing I'm looking for, or until S is empty. Right? So while S dot size is greater than 0, so while S still has some elements in it, right? And not result, so and while result is false, right? I'll pop, right? I'll compare the element that's popped to the one that I'm searching for, right? If it's equal to the one I'm searching for, I set result to true, right? Now when I set result to true, not true is false, right? So you have something and false, which will stop the while loop, right? So setting that to true effectively stops the loop, right? So I'm going to compare, and then I'm going to take the element and I'll push it onto the temporary stack, right? When that loop is done, the original stack is either empty or it's not empty, and so it's either empty, and you found the thing that you're looking for, or it's not empty and you found the thing that you're looking for. Doesn't matter which case you're in, you need to reverse the process. Right? So while there's still stuff in temp, right, pop temp and push it back onto the original stack. Right? And that there's contained. Right? Now notice this is really inconvenient. Right? It's true, I can write this method. Right? But in this case, it would be a lot better if contains was sitting inside one of the stack classes itself. Right? So if you think that users of your stack class might want to have a contains method, you should probably push this into the, you should probably put the contains method in the interface. Right? Because implementing contains for an array is straightforward. Right? You just loop over the elements of the array. Right? There's no need to make a temporary array. Right? Similarly, looping over or iterating over the nodes in a node-based stack is easy. Right? I don't have to make another stack. I just follow the links in the nodes, right? And I can easily implement contains that way. Right. All right. Any questions about contains? OK. Now, for a stack, it's unusual that you would ever use contains. It's pretty unusual. Most stack algorithms are designed so that you only ever need to look at the top of the stack. Right? Or most algorithms that use stacks only ever need to look at the top element of the stack. Right? They don't really need to call contains. All right, utility methods for queues. So we can do the same thing for queues. Right? In other words, I can implement what are essentially the same 4 methods. So let's just quickly go through those. Contains for, the only interesting one here is contains for a queue. Right? That's the only interesting one here. Okay, so again, clear. So how do I clear a queue? Right? Again, notice that it's a generic method. Right? So I have a generic queue here. Generic type variable for the method appears in the front. Right? How do you clear a queue? Well, you just dequeue everything in the queue. Right? So while the queue size is greater than 0, right? Dequeue the queue. So that's easy. Right? NQAll is going to be the same as pushAll. Right? I want to NQ all the elements from this collection, and I want to add them to this queue. Right? Once again, the element type from the collection needs to be the same as the element type of the queue. Right? So how do you do this? Well, you just iterate over the collection. Right? So for each element in the source collection, NQ it into the destination queue. Right? So there's NQAll, and then DQAll is essentially the same as popall. Right? I want, oh, hey, wait, I screwed that up. That's queue. Right? So I want to dequeue everything from the source queue, and I want to add the dequeued elements into the destination. So while the source is not, the source size is greater than 0, dequeue the source, right? And add it to the destination collection. Right? So that's nice and simple. Now, contains is, you're in a similar situation with contains that you are with a stack. Right? So for contains, I want to iterate over the elements of the queue, right? But I have no way to do so. Right? All that I can do is NQ and DQ elements in this queue, right? Because our queue interface and classes do not have an iterator method. Right? Now with a queue, you don't need a temporary data structure to store the elements as you take them out of the queue. Right? The trick with the queue is when you dequeue an element, you just re-NQ it right away. Right? So that's the trick. This works because we know or can get the size of the queue. Right? So I know the number of elements in the queue. Right? So in other words, I can take, if I have n elements in the queue, I can take the n elements out and put them back in. Right? And that ends up restoring the queue back to its original state. Right? So I can write a little loop. Right? I equals 0, I is less than the size of the queue. Right? DQ the queue. Right? Compare the element to the thing that you're looking for. Right? So element equals object. Right? So if not result. Right. So if not result. OK, so if result starts out as false, right? So if I haven't found the thing that I'm looking for, right? So if I haven't found the thing that I'm looking for and the element is equal to the thing that I'm looking for, I can set the result to true, right? Otherwise, I just re-enqueue the element straight away, right? And then you return the result when you're done. right? So that one's a little bit simpler than the stack, right? You don't need the extra data structure. It's still less efficient than if you could iterate over the elements of the queue directly, right? Because if you could iterate over the elements directly, right, you don't have to dequeue them and enqueue them n times, right? That loop always runs for the number of elements that are in the queue, right? Because that's the only way you can restore the queue back to its original state. Right? If you could iterate over the elements, you can stop as soon as you find the thing that you're looking for. Right? So if the thing that you're looking for happens to be at the front, right, and you can iterate over the elements of the queue, your loop only runs once. Right? This one always has to run n times. So again, just like the stack version of contains, if you think users of your class are going to want to ask, does the queue contain an element, you should probably move the contains method to the interface and make users and make the implementers of the queue classes implement contains directly, right? Because they can do so a lot more efficiently than you can here. All right, any questions about generic methods? That's all I want to say about them for now. If there's any classes remaining at the end, I'll come back to this question mark here. Right. So there's this issue of whether or not the element types have to match exactly. Any questions so far? All right. So I guess we'll start lists today. And so the last topic of the course is implementing generic lists. Right? Now in a list, this is a little harder than doing stacks and queues because in a list you also want an iterator. Right? Because you really want to iterate over the elements of a list. So we need to spend some time implementing iterators for lists. Okay, so you all know what a list is, right? So a list is just a finite collection of elements. They're a linear sequence, right? So like a stack and queue. Unlike a stack and queue, though, you can access an element in the list via its position, right? Whereas in a stack, you can only access elements from the top, and in a queue, you can only access them from the front. Right? So in a list, you can access them from everywhere. Now, you've already seen the list interface in the standard library. Right? You've seen the ArrayList class. You used linked list a little bit, but you haven't really seen how it works. Right? Every computing science student should know how all these things are implemented. Right? So we're going to do that now. I don't want to implement the full-blown list interface that Java has, because there's too many methods there. Right? So I want to implement a reduced interface, right? But it's got all the important methods here, right? So size and is empty, we've seen those before, right? I want to be able to get an element from a list via its index, and I would like to replace an element in a list via its index, right? So that's get and set, right? I'd like to add an element to the end of a list, and I'd like to be able to insert an element into a particular location in the list. Right? Java's a bit funny in that it calls, that it uses set for replace, and it uses add for insert. It would be a lot clearer if they had named this method insert and renamed this method replace. But we're stuck with get, set, and add. I'd like to remove an element by its index, so remove the 5th element from the list, for example, and then I want to return an iterator so that someone can iterate over the elements of a list. Right. So there is my interface. Now, in this interface, this is the first time we've seen that. Well, it's the first time we've written this ourselves. Right? You've seen it before. You've probably seen it before if you've looked at the documentation for the standard library classes. Right? So slist, that's our simplified list interface, right? E is our element type, so it's going to be a generic, a generic interface, right? Now this interface extends another interface, right? So in other words, so what this means is that this interface includes the methods from the iterable interface, right? And remember, iterable provides a method called iterator, so it's sitting down there. Right? All of our other methods are here. Right? We have a default method just like we did with the stack and queue interfaces. Right? We have a default method here because we can implement isEmpty using size. Right? So I can just write it here. Right? All right, an array-based generic list. Do I have time to do this? Yeah, sure. Okay, so I've got an array-based generic list. That's where we want to start with. Right? And now this is pretty similar to an array-based generic stack or an array-based generic queue, with the exception, right, that we have to be able to insert an element somewhere into the list, and I have to be able to remove an element from somewhere in the list. Right? And with an array-based queue, something special has to happen in both cases. Right? So I would like to insert into this list. Anything in blue is where an element currently sits in the list. Right? Anything in white, there's no element. Right? So this is an array, right? This is not a list. Right? This is the array that's holding the elements of the list. Right? So your array is always going to be contiguous. Right? There will always be elements one after another, except possibly at the end of the array, where there's still space to hold elements. Right? I'd like to insert a new element at position 4 in the list. Right? So I want to insert an element there. I don't want to overwrite the existing element. Right? I want to insert an element. So what does that mean you have to do? Well, I've got to take the existing elements, starting at index 4, and all the ones to the right of it, and I have to move them. Right? So I got to take those red elements and I got to shift them over by 1, right, to make room for the new element. Right? So that opens up a space in my array where I can now set that element in the array to insert the element. Right? So you now got this problem where when you implement the add method that puts something into the middle of the array, you have to shift elements over to the right. Okay? Adding an element or inserting an element is a little bit weird because most implementations let you insert at the end. Right? So remember, this is going to be add at some index, some element. Right? So most implementations of insert let you insert at the location past the current end of the list, which is weird. Right? Because index 10 in this list is invalid. Right? If you try to get element 10 from this list, you should get an exception. Right? If you try to set element 10 in this list, you should get an exception. Right? But when you insert at element 10, normally that works. Right? Normally that works. Now, fortunately, inserting at element 10 is the same thing as adding to the end of the list. So you don't actually have to do anything special. Right? OK, you just call add. Right? You just call the original add method, and that adds the element to the end of the list. Right? OK, now suppose I want to remove the element at index 4. Right? So removing the element at index 4, right? So I can null that element out, right? But then I need to shift everything that's to the right of it over to the left by 1. Right? So all those elements in red, I need to move over 1 position. Right? Furthermore, I need to return the element that was sitting at location 4. So I need to remember what's sitting in the yellow box right now. Right? I need to take those red boxes and shift them over by 1. Right? And then I need to return what was sitting in the yellow box. Right? But now, again, there's a shift operation that has to occur. Right? So in an array-based list, right, adding into the middle of the list or removing from the list, right, requires shifting up to n elements in the array. Right? So right away, you can conclude that inserting into an array-based list or removing from an array-based list has complexity big O of n. Right? Which means, right, if you have to insert or add frequently into the middle of a list, you probably don't want an array-based list. You probably want something else. Right? So in the next class, we will implement this data structure and hopefully get to the iterator method.